now. I'm also interested a lot in functional programming languages, Haskell as of lately. I work at a company called Good Code. We do web applications, mostly using Django. We also do the occasional CLI tooling, API wrappers, and other non-web related stuff. We have a lot of cool projects listed on our website, so if you like anything you see, give us a call, as we are hiring developers and designers. Let's talk about Docker. What is Docker? The official definition is that Docker is an open platform for developers and sysadmins to build, ship, and run distributed applications. It uses lightweight containers, which is a virtualization technology on top of the Linux kernel. It's available on most Linux distros, provided you have a recent enough Linux kernel on that system. But what is a container? Let's compare a container, a Docker container, with a traditional VM. So in a traditional VM, you would have a host operating system. On top of that, you would have a hypervisor. And on top of that, you would have your virtual machines. Inside every virtual machine, you would have a guest operating system with its own kernel and libraries and applications running in it. Now, contrast that to the Docker way. You have the host operating system, obviously, and the host kernel. And on top of that sits Docker. And on top of that, you have a container. But notice that every container doesn't have a guest operating system in it. It only has libraries and applications running in it. This is because Docker shares the host kernel, which makes it much less, which uses much less resources and less overhead, because you can more easily communicate with various I/O devices, disk, and whatnot. So we established that Docker runs on the Linux kernel. Before going any further, we need to define another term called images. You can think of images as templates for starting new containers. Every container is started from an image. Images are immutable snapshots frozen in time, and you cannot change them. You can add something to an image, but that basically means that you have created another image. And on top of that, you can create another image. And this is done via using a technology called LayerFS. Popular implementations are AUFS and ButterFS, which basically gives you a sort of hierarchy in your image system, kind of like Git. In Git, every commit has a parent commit. In Docker, every image has a parent image. So once you have your image, you can start a container from that image. And notice that the container blocks at the top are writable, but they're transparent. They're transparent for two reasons. First is that, in contrast to a normal full-blown virtual machine, a started container doesn't copy the entire content of an image somewhere on disk, consuming more disk space. This way, it only writes diffs compared to the image. So this way it uses less disk space. Another reason why they're transparent is because containers are ephemeral, meaning that when you start a container, you write your files in the container, but once you stop it, the data is gone. If you restart a new container from the same image, you're starting from ground zero. We can do interesting things with this. We can create multiple images, like a Node.js image, Nginx image, MongoDB image, and they can all have the same parent image. And one point to stress is that you can use your Node.js image and start as many containers as you want from that image. They're not going to share anything other than the same parent image. I wanted to stress this because it's important to understand that it's not a one-on-one relation. You can create multiple containers from the same image. So why should you care? First, it's fast. Container boot up time is measured in milliseconds. Contrast that to VirtualBox, where mostly it's measured in minutes. There's minimal overhead and resource usage. As I explained, you can run thousands of containers on your laptop, but you can run only a few VirtualBox instances. This in turn makes it very easy to run your whole production stack locally, which is a very good idea. So right about now, some of you probably use a Mac and have noticed that I've said that the hard dependency for Docker is a Linux kernel. Thankfully, there's a helper application called Docker, which you can use on your Mac, which basically sets up a small 25 megabyte VirtualBox instance that has the Docker daemon inside, and then you can use the Docker client to communicate with the daemon and spawn containers inside that VirtualBox instance. This is possible because of the Docker architecture. Docker is split into the Docker daemon, which can reside on your laptop or can reside on some host in the cloud. And the Docker client communicates with the Docker daemon via a REST API. So in further slides, we're going to concentrate on one of the clients, which is the command line interface. But there are various other clients. For instance, there are API wrappers for most popular programming languages. And the third component is something called the Docker Index or hub, which is a central repository for sharing images between users, be they private or public images. So let's take a moment and see how a developer would use Docker. What's the flow? The first thing a new user would do is pull a new image from the central hub. He would then start that image and run a new container from that image. You can then start, restart that container, and if it doesn't fit the bill for your use case, you can change that container and then commit that new state to a new image. Notice the Git terminology here. Once you have a new image, you can push that to the central repository, and other users, team members can use that. This is pretty manual. There's a more automated way to do this called Docker files, but I'll talk about that later. So what we've learned so far, we've learned that containers are a lightweight virtualization, that images are immutable snapshots of a container, and that the central hub is a place for sharing images among users. So let's look at a specific example using the Docker command line interface and translate the image we just saw earlier to the command line. You would use the Docker login command to log into the central hub. After that, you would pull an image from the central hub, and you would run that image as a new container. Now, there's a lot of commands and flags here, so let's go into more detail. So how do we run containers? We use the Docker run command. We can run a container in interactive mode using the I flag, and we always need to specify the base image we're using for starting a container. That's the T flag. For here, we are using the Debian image. After that, we specify a command we want to run inside the container. Also, you can run your containers in daemon mode, which is the D flag. And notice that I didn't specify a command when running this container. That's because some images have a default command baked in. So if you don't specify any on the command line, it's going to run that one. There's also a useful thing called tags that you can use to give a version or more semantic meaning to some of your images. Specifically here, I'm telling it to run the Postgres image, but the specific version of that Postgres image. So you can get a list of running containers on your system using the Docker PS command. This gives you an output like this that says this is the container ID. And other useful information. You can use that container ID and feed it to Docker logs, Docker stop, kill command that do basically what you would expect. You get the streaming log output, you can start, stop, and kill your containers. So now that we know about containers, let's see how we can use, for instance, the Debian image and change it to our liking. So there's the manual way, where you would run a new container in your interactive mode, and you would start a bash prompt in it. Then inside the container, you would install your database and configure it. And when you're happy with the result, you would use the Docker PS command, grab the container ID, and commit that container as a new image that's sitting locally on your laptop. And then you would obviously use the hub to push that image to that central repository, so your team members can use that image on their laptops. So the downside to this approach is that it's very manual, in the sense that after 2 months, you're not going to know what the hell you did to create that image. There's no record, and we know that everybody here writes documentation, right? So there's a better way called Docker files, which is basically a DSL for building new images. It tells you stuff like which image is the parent image, and it's a series of steps that tell Docker what to run inside that image and how to configure your service. And once you're done, you can just call the Docker build command, give the new image that's going to be created a name, and point it to the Docker file. This way you have, after some time, you have a nice baked-in documentation of sorts in the Docker file where you see exactly what you did to create that image. Please note that you still need to use the push and pull commands manually to get that new image onto the hub. So recap, we learned that running containers with, is accomplished with the Docker run command. We know that we can build images manually and commit them, but that it's a better way to use Docker files for building new images because you have built-in documentation of sorts for later. So how does this fit into your development environment? So a typical development flow is you start a new application, a new web application, and chances are you're gonna need a database. So you would get a database from a central hub, as we've shown, or build one yourself. And you would start that container. You can then use a client like PSQL or any other client to connect to the database, create your database, user and whatnot, and use your framework of choice method for populating the database with tables and possibly test data. But is this all? How does the client know how to connect to the service inside the container? Well, there's a catch, there's a part missing from here. We need to use the P flag to expose the port of the service running inside the container. You basically tell Docker to map the Postgres port running inside the container to some port on the host, so that when we connect to that service on that host port, it actually works. Another part that's missing from here is, you remember that I said that containers are ephemeral, meaning that when you stop a container, you're going to lose all your test database data, which is presumably a bad thing. You don't want to recreate that every time. So the way we go about solving this problem is using something Docker calls volumes, which basically tells Docker to mount a host directory inside the container to a certain path. This is useful and this works because then Postgres thinks it's writing to warlib Postgres, but it's actually writing somewhere to the host system. So then when you stop the container and start a new one from that same image, you will have your database data retained. This is suitable for your development environment, not so much for production. There's a better way for production. You would use something called volume containers, in the sense that you would just create one container that saves your database data and mount volumes from that container inside your running container, but that's partially out of the scope of this talk. So you repeat this for your database cache queue, and everybody on the team runs the same version of that service, down to the same version of the OpenSSL library, down to the same version of the REC library in the containers. And you only need to do it once. But is there a benefit in running your web app inside a container? Every popular language nowadays basically has some kind of packaging solution, Python, Ruby, where you can list your packages or gems that you need to install in your for this particular project. But everybody knows that this fails apart when you try to install something like an imaging library, because on one workstation you have JPEG headers for the C libraries, and another one you have PNG headers, and suddenly your application resizes images, only JPEG images on one machine and only PNG images on another, and discrepancies like that. So you simplify your runtime, and you can use something called container links, which basically tells Docker to link two containers together in a way that it uses the link flag to give a semantic name of that container inside the Django container, web app container, it enters an etc host entry, so you can reference that container in your Rails or Django settings files, so you don't need to worry about editing the connection string. It also exports a lot of useful environment variables, which again you can use in your settings files. Now this is all great, but as you've probably seen, the CLI is complex. There's a lot of commands, there's a lot of flags, and this is just some of the features I've shown. And not necessarily everybody on your team needs to know how this stuff works to be able to use all those services on their workstations. So basically this is where Fig comes in. It's a new tool. It was initially done by the guys at Orchard, and then Docker acquired them a few months ago. It basically lets you define your containers, basically enumerate them in a nice YAML syntax, and then you have just one command, fig up, which basically starts all those containers, links them up, and if you constructed your settings files correctly, everything will just magically work on every workstation. So the best description of Fig is basically it does for Docker what Vagrant does for virtual bots. So hopefully I've shown you a little bit about how to use Docker, its values, and how it can help you and your development team. And I want to leave you with the idea that you can build your containers once and run them everywhere, be that on your laptop or somewhere in the cloud or somewhere on a bare metal. Thanks. Questions?
Could you just tell us something about your experience with deploying containers in production? So how does that work? Are there any security implications or anything that one needs to be careful about?
At this point, the answer is in orchestration. The answer is mostly it depends. It depends on your use case, because there's a lot of tools which do a lot of the same things but a bit differently, and they're not really interchangeable, and you can't really decide which one to use. If you're if you don't have very cloudish setup in the sense that you know up front how many servers you have and how many containers you're going to be running, Ansible is a good choice to actually deploy containers. There's a module for anything in Ansible, and so there's a Docker module which basically lets you deploy images, build images, deploy images, run containers on your hosts. Yeah.
So I have another question. You said here over here, Deni.
Yeah. Okay.
So you said that you mentioned that you need to have ButterFS and layer FS or something. Do you need to have that on your host machine, or?
No. So that's a bit unclear. So only the kernel that you're running on your host machine needs to have support for those, because that's the file system that Docker is going to use internally in the containers and for imaging and sorts. But you can have a normal ext4 or whatever file system on your host.
More questions?
There.
My question is, what is your experience running Docker containers inside the VMs?
Like virtual box instances?
Yeah. More like DigitalOcean VPS.
Oh yeah. Well, the answer is for DigitalOcean it runs fine, because you have an image that you can just start your droplet, and it already has Docker configured in it. The main issue I think is well, it depends how much you want to automate it. You can use, as I've said, you can use Ansible. To me, it's the most simple solution, which basically SSHs to the droplet and then communicates with the Docker daemon locally there. But if you want to use some solution that's going to communicate with the Docker daemon over the network, meaning you would expose the Docker daemon on a public IP address, you have the issue of authentication. Fortunately, since I don't know, 0.9 version or something like that, there's client certificate support. So your whatever client you're using to communicate with the Docker daemon can authenticate with certificates, so that's
there was an issue, I think, a few months ago where somebody managed to break out of the sandbox and gain write access to host disk, which was supposed to only have read access. So it raised a whole host of questions about security issues around Docker. So can you comment on what's the current state regarding the sandbox and security?
I think I remember the thread on Hacker News that was kind of blown out of proportions, I think. The thing is that that particular case, if I remember correctly, and if it's the same case you're talking about, did some special things. And you can always harden your containers more using like SE Linux or other kernel hardening techniques. So it depends on how much you want to restrict your containers or how much you want to allow them to, because it's not straightforward still, I think. I mean, we're talking about kernel internals here, so most of the users don't do it, but there are certain situations where it's needed, but I guess we could work on documenting those features more. I don't know. I don't know if that answers your question.
I mean, because...
Okay, we're out of time. Thank you, Deni.